So in section 2.3, we're looking at the kinetic energy distribution graph. We looked at potential energy yesterday. This one's kinetic energy. And these two are really, they're completely different graphs. So make sure that you keep in mind which one we're looking at. So here's my axes. Sketch the distribution graph of the kinetic energy of collisions for a reaction at a particular temperature. We're identifying two things, the average kinetic energy for the temperature and the threshold energy. So average kinetic energy is temperature. For those of you that took physics last year, you might have at that point. I'm going to operate like nobody's ignorant. I don't know if I talked to physics last year. So let's say in a sample of a gas, and you don't have to draw this. We've got these different particles, and they all have kinetic energy. Gas particles are all moving. So here's one that's moving with this magnitude or this amount of energy. This one's about the same. This one's about the same. So these are all about the same average kinetic energy. But in this same room, or this box, we probably have one that's going slower, which, as far as kinetic energy is concerned, is colder. And maybe here's one moving slower. But over here, there's one that's moving really fast. Higher kinetic energy, meaning that its temperature would be higher. Maybe another one, say right here. So we have some that are on the average, which would be these. We have some that are above the average, and we have some that are below the average. But the average kinetic energy is the temperature that we read. So when we stick our thermometer in this box, we're not going to see that like these three are 300 Kelvin, this one's 400 Kelvin, this one's 200 Kelvin. You're not going to get a reading like that because they're so small and there's so many of them that we're really getting a reflection of the average. So when we look at this in terms of a kinetic energy graph, it's a normal distribution. So if this is the normal distribution, here's the average kinetic energy, which is the temperature. And there's this idea of threshold energy. So let's draw another line. I'm going to put it about right here. Threshold energy. So we're talking about collisions, we're talking about reactions happening. What do you think threshold energy is referring to? Probably goes back up to the top. A reaction takes place when three things happen. One, molecules collide. That's going to happen either way. Number two, with enough energy. So what this is really telling me is that only molecules that have this much energy or more are going to be able to react. And that would be these ones down here. So if we want more of these to react, what are we going to do? Remember there were 5 things we talked about speeding up a reaction. So we can increase the concentration, we can increase the pressure, increase the surface area, add a catalyst. or we can increase the temperature. And by increase the temperature, we're talking about increasing the average kinetic energy. And this is going to look like one of those flattening the curve things. So, I'll use purple for this one. We're still going to have some that are way down here, but now we're going to have some that reach all the way over here. So our normal distribution is going to take up more of this x-axis, but as we stretch it out, we end up with this flatter curve. So on this purple curve, where is my average kinetic energy? It's say the average kinetic energy is here. Which is the temperature. Look, we increase the temperature for the average kinetic energy. And now look at how many of these molecules are beyond that threshold energy. Now we've got all of this instead of just this. So beforehand, we had maybe, 5% had enough energy to react, and now we're looking at almost half has enough energy to pass that threshold and actually react. So if I were going to draw this one as a box, so I would probably still have a couple that were along the lines of the old average. But now most of them are probably moving much faster, like this. Here's the old average. And look, there's still a few data points that are way down here. So one of these really slow moving or low energy particles still exists. There's still some of them there. There's just maybe fewer of them, shown by the height of this curve. And there's a lot more of these bigger ones that are driving the average this way. There might even be some that are moving extremely fast. That would be like maybe one right here. It has a lot of energy. So it says use a dashed line to indicate what happens when catalyst is added. We've probably already got a bunch of dashed lines on our paper. So we're going to want to break them. So I'm going to make the catalyst green. Here's the original threshold energy. What happens to a reaction when we add a catalyst? It speeds up. And it speeds up because it requires less energy to get started. Look back at this graph right here. The activation energy was higher originally, adding the catalyst made it less. That's what it looked like on the other graph. What that looks like on this graph, it moves this threshold energy to the left, maybe here. So there's my catalyst. All it did was move that line to the left, and now, even if I didn't increase the average kinetic energy, look how many of these blue ones are able to react. A lot larger number. And look what happens when we add the catalyst and increase the average kinetic energy, we were able to get all of these ones to react as well. So this question, from this graph, why does the addition of a catalyst speed up the reaction? Put this in your own words if you want, but all right, my answer now. Catalyst lowers the threshold energy. This is what it does. How is it affecting it? So more molecules collide with enough energy or with sufficient energy. To form, it says the transition state, basically your products. From this graph, why does an increase in temperature speed up the reaction? When temperature is increased, moving and colliding with more energy. When it comes to definitions like this, you're going to want to be able to put these in your own words. So like if you saw a picture of this graph on the test and it asks you the same question from the graph, why does the addition of the catalyst speed up the reaction? You would want to be able to, you want to understand the stuff that you're explaining. That's what it is. Because chances are you're not going to memorize this definition. And if they asked you on May 7th, what happens here, you just need to be able to explain that. Question, right? I like the 5 days a week either. It's making my throat scratchy. Have to talk too much.
The last couple of years.
Huh?
What you did the last couple of years.
Well, I got a hacking cough the second week of school every year, and the second week of January every year, and then I was fine. But if I get a hacking cough now, I'm going to have to miss 14 days of school, and then come back, and I'm going to be nice and fresh in my throat, so I'm going to get another cough. I'll miss another 14 days of school. It'll be like a vacation.
So you should practice on start talking to
Talk more at home.
sit your kids down on TV. Teach them basic chemistry.
Well, the amount of yelling at home is not changed. Something about toddlers and kindergartners, they just don't under your ears. Or if they can hear you, they just don't understand.
Like,
Boys don't learn, men don't know. Yes, If you have questions, we'll talk about
That's good.
it. Alright, so the Arrhenius equation, not something I want to talk about in this unit. We'll talk about it in the acids and bases units and a couple other places, but right now.
Yeah, on the field test.
I mean, this is really kind of one of those derived formulas kind of things where like I can tell you about it and I would confuse all six of you. Then you ask me questions. Basically what it's talking about is relating activation energy with the addition of a catalyst. And yeah, in this form, it's not even on the exam. Moving to reaction mechanisms. Okay, so out of the six of you, two of you worked on the APD 2010 number 3. The rest of you will be looking at it later today. There is the very last question. It says, I'll just pull it up and look at it. Hang on. Very last question. It says, is it likely that the reaction occurs in a single elementary step? Justify your answer. We talked about one sentence of it in section 1, and then we just moved on. This is really a unit 3 kind of question, but it went in with the rest of this EP question. So chances are, if you did this yesterday, you have no idea how to answer this question, and it was not in the submission form of question anyway. But this is where we're addressing it now. It's reaction mechanisms. Chemical reaction depends on particles colliding into one another. A two-molecule reaction such as A2 plus B2 yields 2AB could occur in one step. And you even got a drawing here. So two molecules, and you've got some little arrows here that are coming in towards each other, and we end up with something that looks like this. And then we end up with this. In Chem 1, we always pretty much pretend like we have these two things, they reacted, and then here's what happened. But there's usually something going on in the middle. It's not just like magic where the two things touch and then they're matching two other things. There's actually atoms there and they're being rearranged, just like we've always said. But these two molecules collide with enough energy and they kind of stick together for a minute. And this is an unstable product, intermediate is what we call it. Since it's an unstable product, it's going to break. And it breaks into these two different things. And so we would normally treat it like A2 plus B2 equals 2AB. Now we need to start talking about what about this transition state in the middle, this unstable thing that forms for, I don't know, maybe it's there for a half second, maybe it's there for 20 seconds, who knows. Example 1, a reaction involving more molecules, such as or HBr plus O2 yields 2 waters and 2 bromines. A reaction involving more molecules, such as this, would be amazingly slow if we waited for all molecules to collide, 1 at the same place, 2 at the same time, 3 in the correct orientation, and 4 with enough energy to react. Because you're waiting on 4 HBRs and oxygen all at the same point in time. It doesn't really happen like that. Instead, one collision of 5 molecules, it happens in 3 different steps, or what we call elementary steps. So you can see it here on your page. Step 1, we have 1 HBr coming in contact with 1 O2. And we end up with this. I'm just going to say it out loud. Step 2, what we have is the product of the last step coming in contact with another HBr. And now we end up with 2 of something slightly different. And then the third step, where 2 of those products of step 2 come into contact with 2 other HBRs. And this is where we get our 2 waters plus bromines. Seems like a lot of work done. So this is more what's reflected in what's actually happening. So don't cross anything out yet, but I'm just going to do this to illustrate. 1 of these and 1 of these. 2 of these and 2 of these. If we were just to add all these together, we end up with the actual thing that we wanted. 1, 2, 3, 4 HBRs plus 1 O2 yields 2 waters and 2 molecular bromines. So it happens in 3 steps. You'll also, off to the right, see something else. It says that step 1 is slow, step 2 is fast, and step 3 is fast. And this tells us something about the kinetics of the reaction. So there's a little story I heard at a chemistry conference 2 years ago. It's imagine that you have this cake factory where they make cakes by hand. And so you've got 3 stations. You've got the person who mixes up the batter, you've got the person who bakes it in the oven, and you've got the person who puts on the icing. So the person making the batter can make a bunch of batter, slide the bowl over, make a bunch of batter. They're pretty quick at it. They pour in the flour, the milk, and all the eggs and stuff, and they just make a bunch of batter. Is that a fast step or a slow step? It's kind of fast here. Then you've got the one who's baking in the oven. Let's say they've got a single oven for some reason in this cake factory. And so the person pours the batter in a pan, they put it in the oven, and they let it cook for 20 minutes. That's the slow step. And then you've got the next step, which is the icing person, and they have this big bowl of icing. They come over here and they put it on, and then the cake's done. Well, the person making the batter is just constantly making batter. There's way more batter over here than there is cakes going in the oven. This is a fast step. The oven is a slow step. We're waiting on this guy. This guy could take a break if he wanted to, the one making the batter, because the cakes aren't going in the oven fast enough for it to matter. This batter is just sitting there on the counter anyway. If you look at the icing guy's gonna take a lot of breaks, because he's standing there waiting on the oven for the next cake to pop out. So if it takes him 10 seconds to ice the cake, or even 5 minutes to ice the cake, if it takes 20 minutes to bake it, he's got 15 minutes between every single cake that he can just sit there and do nothing. For the sake of this, yes, only one. For some reason, this cake factory only has one oven that can do one because it seems like a little investment in ovens would make this much more productive. But that's the problem. We've got a fast step, we've got a slow step, and we've got a fast step. Which one is determining how fast this cake can be made? Slow step. The slow step is the one that always determines how fast this reaction can go at all. And so it's always this one. Whatever the slow step is the one that determines how fast we can make the products. Because we're waiting on HBr and O2 to make Cooper. If that takes forever, we can't move on to the next step until we have a couple of these. So we're constantly waiting on this one. Let's pause there and pick up on it tomorrow.